First up this morning, we've got Chris with the second lecture. Over to you.
Thank you and welcome. Good morning, everyone. So today I'm going to talk about two aspects of early universe cosmology. More about the second than the first, but one part is a theory of origins, as I was talking about in more general terms yesterday. That would be a theory that regards the origins, the initial singularity, and it's relatively unambiguous that we need some insights from quantum gravity there. But a lot of cosmology has been dominated since around 1980 by a discussion, an idea called inflationary cosmology. And that's the idea that there is a phase of exponential expansion driven by an inflaton field phi. And one of the questions I want to address today is to what extent, sort of indicate it's not something that is new for me to address, but obviously there's been a lot of discussion of this. To what extent is the idea of inflation independent from assumptions about origins and quantum gravity? So to what extent can we treat this as a dynamical phase that we can treat separately with physics from a lower energy scale, and to what extent does it involve assumptions about quantum gravity? And in particular, this could involve both, is there a plausible description of a pre-inflationary state? How can we assess that? And then how do we describe the inflationary dynamics? And one thing I should mention before I go on, it was on my opening slide, but this is, reflects work partly done in collaboration with Adam Koborinsky. I should also acknowledge that the earlier talk was partly done in collaboration with Jim Weatherall. So I forgot to mention that last time. So as an outline, a lot of the opening of the talk, and perhaps more than half of the talk, is going to be focused on inflation success stories. It's actually a very phenomenologically successful theory, and I want to describe that in some detail, taking a slightly historical approach, and also give a characterization of the sense in which inflation is empirically successful, because I think it's phenomenologically successful, but one of the themes running through the talk is that there's persistent issues and problems that have been posed since the very early days of inflation, which are still, to my mind, open and interesting questions about it. And so then after that discussion, I'll turn to inflation as an effective field theory, which is sort of the contemporary way that a lot of inflationary advocates describe how we should think about inflation, and I'll ask some questions about how consistent that account is. So very quickly then, the sort of standard lore about inflation that you'll encounter in any cosmology textbook. The idea, very simply, is that the universe went through a phase of exponential expansion that's driven by a scalar field. So the stress energy tensor for a scalar field includes derivative terms, but if you have a sufficiently homogeneous patch of the scalar field, those derivative terms will be negligible, and the gravitational impact of the scalar field will just be to contribute this effective potential term, that's the V phi multiplied by the metric. So if you have an equation of that form, then that will eventually lead, and this is there's cosmic no-hair theorems that try to make this claim precise, but the idea is that if you have a term like this, along with whatever other contributions you have from stress energy tensor from other fields that might be around, this field will dominate the expansion. Effectively, other fields will be diluted away. So radiation of matter will be diluted away either as the inverse cube or the inverse to the fourth power of the scale factor. But an effective cosmological constant term will stay constant, so it will continue to contribute to the stress energy, and it will eventually come to dominate. And if we have an exact solution which just has this term, it would be a de Sitter solution. So the idea is that inflation, because this will dominate, will eventually approach a quasi-de Sitter-like phase. And so more loosely, we could say, and sometimes, there's some ambiguity in what we mean by defining an inflationary phase. So some people take the more loose definition as just a phase where you have accelerated expansion, not necessarily exponential expansion. So there are some models of inflation that have slower inflation, but the simple idea is that you have a phase of exponential expansion driven by this false vacuum energy. And again, this is just the standard lore. What does this do for us? So the image on the top, I don't know how clearly you can see it, is a representation of the horizon problem. So if we're on the world line O, if we look at our past light cone, there would be 2 points on the CMB, P and Q, whose own past light cones do not intersect. And so this is why there's a uniformity puzzle in the standard Big Bang cosmology. How is it that the temperature that we see from those parts of the sky and their other physical properties are all very similar if they don't have an opportunity to causally interact? The flatness problem, if you look at the left-hand side, on this graph, the x-axis is the scale factor, and the y-axis is omega, the density parameter. And I'm sorry, you probably can't see this that well, but the lines diverge. The horizontal line is omega equals 1, and you can see lines diverging from that as you go to increasing scale factor. So what that represents is that if you started anywhere away from 1, either above or below, you rapidly diverge from 1. Now, on the left-hand side, that's just the standard FLRW expansion, right? The standard Big Bang model dynamics leads you to rapidly diverge from omega equals 1. Now, the inflationary resolution of this problem is by changing the causal structure of the early universe. For the top diagram, you can think of that as just dropping the bottom surface, the bottom t equals 0 surface, to be much further away. So you stretch the distance, and that allows those 2 light cones to overlap. And by changing the dynamics, you reverse the kind of dynamical behavior of omega as a function of the scale factor, and that's what's reflected in the right-hand side, where you have the curves now driven towards 1 during the phase of inflationary expansion, rather than away from 1. And so this is, again, this is the sort of textbook presentation of inflation. This is the sort of argument that Guth originally gave that's repeated quite often now, that the fine-tuning problems are solved by stretching the horizon distance and taking and driving omega towards 1 during this inflationary phase. And so the argument is that after an inflationary phase, you'd expect a uniform, flat patch for a sufficiently long inflationary phase. Now, I've rehearsed this, but as you know from last time, I'm pretty skeptical of this as the proper way of thinking about fine-tuning problems, right? So I think this reflects the kind of treatment of probability and historical inferences which I criticized last time. So I don't think this is actually a particularly compelling case for inflation, although sociologically it was obviously incredibly compelling, right? It helped launch a field. Guth helped launch a field by making a case in this form. But there have been, again, since the very beginning of inflation, so Penrose first lodged complaints about this form of argument starting in the early 80s. He's continued to do so, and there's a nice presentation in his book, Road to Reality, that he's made this point several times at different places. Sean Carroll has also argued that the probability assessments involved in thinking about these fine-tuning problems are problematic. So I think this kind of case for inflation, although it's still the thing that you would encounter in a textbook, or probably have encountered in textbook treatments, is really not all that compelling. But I think there's a different kind of account of inflation, which is based on a different aspect of the idea, which has been important in how inflation has interacted with observations over the past 40 years. And so one of the things that has been important in the history of inflation since 1980 is that starting in the 90s, there have been a series of observatories, and this is just the space-based observatories that are more prominent. There's also been ground-based observations, which look at the CMB in more detail, and there's been a very fruitful interplay between inflation and these observations. So in particular, after inflation was introduced in the 80s, there was another idea that arose, which is that inflation could give a causal account of the formation of structure. That led to a very clear set of predictions for what you would expect to see. Well, I'll come back to whether they're predictions or not, but there are expectations about what you would see in the CMB. And then we have a series of observations which are related to the phenomenological properties of inflation. And we can see that each of these large observatories, Kobe, WMAP, and then Planck, each of them were motivated in part by constraining or determining the details of inflation. So, and I think this is reflected in some of the literature. So I said that I don't think the fine-tuning case is as compelling. You do find people making a similar point in the literature. So this is Andrew Little and David Lith. This is a textbook treatment of inflation's account of structure formation. They unfortunately use a kind of Popperian framework for discussing this, but they say these problems, the fine-tuning problems I just rehearsed, can no longer be regarded as the strongest motivation for inflationary cosmology because it is not all clear that they could ever be used to falsify inflation. By contrast to inflation as a theory of initial conditions, the model of inflation as a possible origin of structure in the universe is a powerfully predictive one. Different inflation models typically lead to different predictions for observed structures, and observations can discriminate strongly between them. Inflation as the origin of structure is therefore very much a proper science of prediction and observation. So let's see how to cash out this idea and how has it played out in the history of inflation. So first of all, let's go back to a pre-inflationary point, which is that prior to inflation, people who had discussed structure formation had realized that in order to have an account of how structure originated in the universe that's compatible with what we understood about galaxies and their distribution at that point, and also if you accept that galaxies form by the growth of initial perturbations through gravitational enhancement, you can actually, in some sense, take what we know about galaxies and run that backwards to determine what would be a reasonable set of initial perturbations. And so there are three authors, I think independently, who all characterized what kind of perturbation spectrum would be compatible with what we knew about galaxies at that point. And so this is a diagram from Sunyaev and Zeldovich. And I don't think it's useful to go through the diagram in detail, but what they're showing is just what the consequences of a scale invariant spectrum would be. So scale invariant spectrum means that there's a fixed amplitude for the fluctuations as they cross a particular scale. And the striking thing with what they're showing here is actually that you'd have acoustic oscillations. They're also realizing that there would be an imprint on the CMB as an outcome of these perturbations. But there were a few features that were recognized as things that you would just need to have as a viable set of initial conditions for an account of structure formation. The first is that there's a scale invariant spectrum of adiabatic fluctuations, and that would give you an overall correct spectrum for the formation of galaxies, and it gave you an estimate of how big these would have had to be at the time that the CMB was created. So that's T-REC recombination. So it gave you an estimate of how big these perturbations should have been at that phase of cosmic history. And they had to be standing waves that were scales bigger than the Hubble radius. So the Hubble radius is a way of estimating the length scale of causal interactions, local interactions in the early universe. So the fact that these would have had to be standing waves at super Hubble scales raised the question of how they could have been produced. So how could you have coherent standing waves that were at length scales greater than what seems like the appropriate length scale for causal interactions at that time? And finally, they, again in the 70s, they already had indicated, and that's the graph of from the Sunyaev and Zeldovich paper, they recognized that a set of perturbations with these features would leave an imprint on the CMB in the form of acoustic oscillations that we could see in terms of temperature anisotropies in the CMB. And also, although I don't think they used this language until quite a bit later, that there would be oscillations that you could see in the matter spectrum if you could observe the distribution of galaxies at slightly later times. So they both had the prediction that there would be these initial perturbations and some of the consequences of them. So, but as I said, there's a kind of mysterious aspect of these perturbations, namely, it's not clear how they could be produced causally, given that they had to be standing waves at super Hubble scales. And one of the great successes of inflation was that it provided a way of giving an account of the origin of these fluctuations. And so, again, I'm sorry, these are probably not that easy to read. There are two figures here. The bottom one is in terms of co-moving scale. The other is in terms of physical scale. And the key thing is that during inflation, given a fluctuation mode with some length scale associated with it, so pick a fluctuation mode, you have this characteristic horizon exit and re-entry that these figures illustrate. So what that means is that you have a fluctuation that starts at a scale below the Hubble radius, so it's a locally characterized fluctuation of a scalar field. You then have it stretch during inflation, and the mode scales so that it goes over, so the Hubble radius in effect stays constant during the inflationary phase. And so the mode stretches beyond the Hubble radius, and then later, after the inflationary phase ends, the Hubble radius starts to grow faster than the co-moving length scale of the perturbation, and so then it re-enters at some later phase. Now, the key thing that's important about this is that the dynamics during those two phases of evolution are different. And this is just described by something called the Mukhanov-Sasaki equation, which shows that the evolution of these modes are different when they're sub-horizon and outside the horizon. And that leads to, while you're outside the horizon, the state's being squeezed. So the overall picture is that you start with a dynamical evolution below the horizon scale, that then gets squeezed as it goes outside, and then it re-enters with properties that are appropriate for the formation of structure later. So you can end up with a causal generation of something that, before this looked puzzling, you can have a causal way of generating scale invariant spectra. And so then the details of the model will lead to specific predictions for the properties of the spectrum that's produced. So NS and R are two. So NS characterizes the perturbation spectrum that you get as an outcome. Whether it has blue tilt or red tilt, that means how much power it has as a function of different scales. And R is something that relates scalar and tensor perturbations. So I've described very roughly, obviously, what happens to scalar perturbations, but you can also ask about other types of perturbations, namely tensor perturbations. And if they're produced by this mechanism, there'll be a fixed relationship between the scalar and tensor perturbations. And so the outcome will depend on the state of the field and the shape of the potential that's driving this process. So again, this was realized relatively soon after inflation was discovered, that there was this technique or this way of giving an account of structure formation. And I should emphasize that this is all the evolution of the inflaton field, so it's vacuum fluctuations of the inflaton field that are being stretched and squeezed during this process. So the early inflationary models were driven by specific candidates, specific proposals for what this field would be, and this was the 80s, so they were drawn from grand unified theories. But the consistency with the accounts of structure formation demanded that they couldn't, that the field driving the inflationary stage could no longer be identified with really plausible particle physics candidate fields. So in particular, I mentioned before that as of the time inflation was proposed, there was an estimate of how big the perturbations would have to be at that phase of the universe to lead to galaxy formation. So I gave you an estimate of the amplitude of the fluctuations. Now, if you take the inflationary account of structure formation, you can then reverse engineer and say if the amplitude matches this observational constraint, what can I say about the properties of the field driving the inflationary phase? And it turns out that getting the amplitude right meant that you had to rule out all the plausible particle physics candidates at the time. And so fairly quickly, this was in the early 80s, people started talking about the inflaton rather than a specific Higgs field that could drive inflation, where the inflaton was now a particle physics field that was introduced in order to drive inflation. And the question of how it was connected with other candidates in the particle physics menagerie was left open. And it was unclear whether you could find a model from particle physics that would actually have all the properties that are required for the inflaton field to work. And I should say, just as an aside, there's a lot of people who claim that one of the main features of inflation is that it gave a successful prediction for this picture of structure formation, that inflation predicted that you'd have a scale invariant spectrum with a number of other features. And it's not actually clear to me that this is, for the people who follow the general philosophy of science literature, really a case of prediction or accommodation, in the sense that it is the case that there are features that seem to be quite generic for inflationary models of the spectrum. But it's also the case that you had to modify the inflationary models in order to accommodate what was known as, in terms of empirical constraints at that time. So it does to me look like it's a kind of borderline case, whereas in the physics literature, this is often presented as just a clear case of a successful prediction. Okay. So we then have, as Little and Lith indicated, that this is one of the more promising aspects of inflation. And I would say that if this hadn't developed, inflation might not have attracted the kind of attention that it has over the last 40 years. It's really the causal account of structure formation that is the working aspect of inflationary cosmology and the source of all of the comparisons with observation. So again, just to give a brief summary, the causal account of structure formation then says that the fluctuation modes at cosmological length scales, the things that generate galaxies, can then be generated by local physics in the pre-inflationary state. So that's appealing. And in their later evolution, they're squeezed at super Hubble scales, leading to nearly scale invariant spectrum. And then that can be preserved through subsequent evolution. I put a small question mark here because there are some accounts of later phases that might modify or damage this feature, but I think for most inflationary models, this is something that is preserved later on. So once these seeds are imprinted, later evolution of the universe doesn't change them dramatically. Okay, so is inflation the only game in town? So it's dominated discussions of the early universe, but I think it's important to remember that especially in the 90s, inflation had an important competing theory. And this is something I'll just describe really briefly, that there was a different account of how to think about structure formation through topological defects formed in phase transitions. And currently, there are also a number of competing ideas that I think we'll hear more about in Mary's talk, about how to think of early universe cosmology in very different ways that don't involve the inflationary stage. But I think it's interesting to say something briefly about how this contrastive evaluation developed in earlier cases. Again, as a general philosophy of science point, I think we often use a contrastive context to both isolate what's interesting about a theory and then to give us a well-defined empirical or observational program. And in the 90s, that was the contrast between inflation and topological defects. So just very briefly, topological defect theories there were a variety of them, depending on exactly what kind of defect formed. But over the course of the 90s, so you could have strings, textures, monopoles, all kinds of different defects that would form during phase transition. And over the 90s, there was a consensus developed that even though to find the specific details of one of these defect formation models, it was quite challenging in some cases, there was a quite general contrast between how structure formation worked in these defect models and how it worked in inflation. And here I've summarized, this is from Albrecht's paper, and there's a figure from that paper as well, that really defects were a kind of active structure formation in the sense that you create a network of defects, and those continue to source gravity. They continue to contribute to the stress energy tensor, and it's a very difficult nonlinear problem, and you have mixing across different length scales, and so that's why I say it's sometimes described as decoherent because you have mixing across different modes. So it turns out to be a very difficult calculation in detail, but there are some clear contrasts. This is an illustration of a particular model of cosmic strings, and this is the prediction for the power spectrum. On the x-axis, you have the L, the y-axis shows a measure of the amplitude. And so the dashed line represents the string model. And what you see is a single peak at a much higher L and no acoustic oscillations. And that's fairly general for these structure formation models based on defects, that you don't see the kind of acoustic oscillations that you'd expect from inflation. So inflation, on the other hand, was described as a passive account of structure formation. There's no active source term, and the modes each evolve essentially independently. So you just have an equation, the Mukhanov-Sasaki equation just governs the evolution of each of the Fourier modes, and those are evolving independently. So you have a quite clear contrast between these, and it turns out that by the time of the WMAP observation, so this is the Planck observations, which are even more clear, but the WMAP observations already showed the structure here of having acoustic oscillations. So obviously this is about 10 years later, but even the earlier results showed the structure of acoustic oscillations, and that effectively rules out the defect formation models. And you also, it's a different parameter here, but the L is on the top here, and you can see that the L is at a very low value compared to what you'd expect from a defect formation model. So, so inflation succeeded, and the way of characterizing inflation now, one way of characterizing it, so inflation succeeded, but there's also almost an embarrassment of riches in inflationary modeling. There's several hundred models of inflation. So people actually complain about the difficulty of finding a name for a new model because all of the funny pun names are taken. And so, so one way of approaching this question when we have this huge class of possible models is the approach taken by Jerome Martin and collaborators. They call it the Encyclopedia Inflationaris. And they don't even, they even have to say that they haven't classified all the models available at the time. They classify around 200. They group them into different categories, different types of models, and say, in each of these cases, so I've emphasized before that the inflationary models basically involve introducing a scalar field with an effective potential. There also has to be this last term, which is just an interaction Lagrangian with everything else in the standard model. That's because we have to reheat the universe after the end of inflation, so that means it has to decay into all the other particles of the standard model. So we have to include a term that characterizes those interactions as well. And so inflation we can characterize as this huge space of models, and we can then, the way that Martin et al. Approach this is to say, which of these 74 classes of models are actually preferred by the Planck data? And so what they end up with is, this is a little bit hard to read, but it's meant to indicate confidence intervals for different types of models. So if you just focus on the very bottom, there's a kind of set of green dots there. That's one that's very high within their preference. So again, they have a way of characterizing how the evidence prefers these, and these are meant to be confidence intervals for those assessments. And the different lines indicate including different aspects of the Planck data, and I think in some, yeah, they also have evidence from BAOs and other kinds of cosmological observations. But the green lines here correspond to actually the earliest model proposed by Starobinsky before Guth, and that's one of the most preferred models. So they're able to say, of this huge space of models, which are the ones that are most highly preferred by the evidence. And so overall then we have the phenomenology of inflation, the picture that we have. We can ask what parts of inflation are constrained and how are those constrained? So as we've just seen, taking the middle line of the structure formation, there are different ways of characterizing this, but one way of thinking about it is that we have a function, the effective potential, that describes the evolution of the inflaton field during this phase. And the account of structure formation, namely how does it create these perturbations that are then seen in the CMB, depends on the value of that potential and its first and second derivatives. And so the constraints that we're putting are basically on one part of that effective potential, the part where the relevant modes cross the horizon. The original things that Guth emphasized really don't tell us that much about the details of inflation. So if we ask, what do we learn about inflation from the fact that it solves the horizon and flatness problems, that really only puts a lower bound on how long the inflationary phase lasted. Right? So I've been critical of these as motivations for inflation, but if we just ask, how much do we learn about the details of inflation by the fact that it solves these problems, we really don't learn that much. So we learn more about inflation as a solution of the structure formation problem, but again, it's really, there's one part of the potential, the part where the relevant modes cross, that we learn about its first and second derivatives. We could learn more. There's been attempts to discover non-Gaussianities. Some of the cosmologists here might be more up-to-date than I am, but as far as I know, there's still no detection of non-Gaussianities. That was something that people were maybe hoping for with Planck. I don't know if there was ever really that much optimism, but that would also be revealing. And finally, if we discovered polarization in the CMB and were able to B-mode polarization, we could use that to test the scalar to tensor ratios. There's prospects for ongoing tests, again, based on the kind of structure formation. And finally, there's this aspect of inflation reheating, where, again, during the inflationary phase, everything but the inflaton field gets diluted away. And since we don't see an empty universe, we have to repopulate it. And so that's when you have to incorporate this interaction with all the other standard model particles. Again, the people who know cosmology better than I do can update me here if I'm wrong, but my impression is that there's very few direct observational constraints on this phase, other than you need to recover the sort of energy densities and radiation density that we use in the standard model. So what I hope I've conveyed is that there's phenomenological success here, but in some sense there's quite a bit of looseness, right, in terms of how well the observations can be used to constrain the inflationary field. So if we really take the inflaton as just a field that we've written down, we have a function here, v of phi, and the interaction with the other standard model fields. If we treat those as unconstrained, then we really haven't done that much with observations to constrain those. Obviously, if we had a particular particle physics model, or a stronger set of constraints from fundamental physics, it would be a different story. And that's why I say it would be much more interesting if you take a specific model of inflation that is identified with a specific field or a specific idea from fundamental physics. You then have a source of other constraints, namely, how does it fit into the fundamental principles, or are there observational constraints that you can then bring to bear as well? So I think I'm very much in sympathy with this comment from Steven Weinberg. He says, the consistency of observations with the large class of inflationary models is encouraging because it supports the general idea of slow roll inflation, but also disappointing because it shows that these observations so far do not really tell us anything specific about the details of inflation. With further improvements in experimental precision, we can look forward to a more decisive test of the theories of the early universe. And I think we're still looking forward to that. This was written before the Planck data came in, but I think it's still the case that we really are looking for a more decisive test that really allows us to say more about the details of inflation. And here I think it's useful to just look at historical cases. And in other cases in physics where we've asked for a more compelling argument in favor of a theory, it is getting the details right that matters. And so what the form that this often takes is not just constructing an initial model that's compatible with some domain of phenomena, but going further than that and constructing a more and more detailed model through successive approximations. And then discrepancies from observations can reveal where you need to add further details, and you can ask whether those details are compatible with the underlying principles that are guiding your inquiry. And so I think you can see this happening in celestial mechanics, for example, that over 250 years, this is what George Smith describes in his 2014 paper. You can see that Newtonian gravity was tested not just by the initial case that it made sense with respect to Kepler's laws and what was known about planetary orbits in 1687, but it continued to guide inquiry for 250 years, where it was incredibly fruitful to assume that all of the motions in the solar system were due to the force of gravity, and that gave you a way of both understanding observations at a particular point and anticipating what would be interesting to look for further. And so I think when we ask, in other cases of physics, what is it that really gives us a way to respond to worries about whether our theories just fit the data by being flexible? You say, well, part of it is that it doesn't look like it's merely a curve fit because it's been so useful in guiding inquiry in this sense. Right? So as you use a theory in that sense, I think you get more and more evidence that you've actually captured something that's important about the physical regularities in nature, rather than just using a flexible theory that you can use to fit the data. And also, it gives you a way of assessing and contrasting the theory at hand with competitors. So to make the case that the theory is better, if you're able to show that it's led to productive inquiry in this sense, I think you can make a case that it should be taken as superior to other competitors that just happen to fit the data. And so in line with what Weinberg said, I think that the kind of case we can make for inflation now, it's a strong case. Obviously, it's succeeded where other attempts to give a theory of structure formation have failed. But I don't think we have the kind of detailed case that we have in other areas of physics, because we haven't made the step of including observations and refinements in a single model. Instead, we can sort of always just go back to the first step and define a new inflationary model as we have new data coming in. Okay, so yeah, so this is, and the reason why I think it's so difficult is really that there's an unclear connection to fundamental physics. That inflationary model building is not really tightly constrained by other ideas in physics, and that gives us a flexibility in exploring the space of models. That makes it harder to say that we've undertaken this kind of inquiry that's tightly constrained. And I'll say a little bit about a few foundational challenges before turning to the conception of inflation as an effective field theory. So a lot of you might have seen this debate that was very prominent. It's now quite a few years ago. There's a follow-up paper after this one, which is called Pop Go the Universe, I think, something like that. And so this was a series of papers. This one's by Steinhardt. The others are by Steinhardt, Anna Ias, and Avi Loeb. And they provoked quite a controversy. It turns out telling scientists that the theory they've worked on for 3 decades is not scientific is a way of provoking controversy. And so they had a very polemical article in Scientific American, which the response was, I believe, organized by David Kaiser, a group of 42 or 46 prominent inflationary cosmologists writing in and saying, what we're doing is perfectly scientific, thank you very much. I didn't want to go into that debate in detail, but I think there's a few issues that they're highlighting which are useful, even though there's a very polemical aspect of the debate, which I think is not so useful. One of the things that they argue in the later, not this paper, but in the later paper, this was after the first round of the Planck data had come out. And one of the things that they asked, so I showed the graph earlier of the models favored by Planck, they asked, how plausible are these models? You know, so we can say, here's a space of models, the data favors this one. But they asked a further question, should we take those models as plausible? Are they actually, you know, models that we should be happy with? And this is related to the background question, what is the inflaton? If you ask, how do you fill in the physical account of what this field is there a plausible way of filling in that story? Secondly, what's the plausibility of the pre-inflationary state? So they were worried that some of the models that seemed to be favored by Planck actually required very unusual initial states. So that was one of their arguments as well. I'll say more about the flexibility of the, I mean, I've already said enough probably about the flexibility of the inflationary paradigm. That's another theme they emphasize. I actually think the main issue that they raise is one that I'm going to mostly set aside, which is this question of eternal inflation. So I'll say something very briefly about this, but the eternal inflation arises if you consider what happens to inflationary dynamics and sort of extrapolate backwards and ask more about the initial conditions for inflation. And some ways of extrapolating the kind of account I gave earlier of slow roll inflation back to earlier times suggests that all of the region we see, the sort of everything we see within the Hubble radius, we can think of that as one bubble that stopped inflating, but that if we think of the dynamics on more global scales, overall the universe and other regions should be continuing to inflate with small bubbles that stop inflating sort of periodically appearing. So we happen to be in one of the bubbles that has stopped inflating, but elsewhere in the universe at the global scales, we'd expect things to look radically different. One of the reasons I'm setting this aside is that I think the arguments, so there's a lot of people within inflation who think that inflation is generically eternal. That means given any model of inflation, you'd expect it to lead to eternal inflation. I think those arguments are sketchy at best. I'd be interested to discuss those further if anybody has more insights on this. But the arguments involve extrapolating the dynamics for inflation to domains where I think it isn't clear that we should trust it. If you accept that inflation is generically eternal, then I do think you have a set of questions about how to think about inflation more broadly. And these are the questions that Steinhardt, Eos, and Loeb really take and use to criticize the contemporary consensus. So they argue that if you accept eternal inflation, then there's a number of questions that you have to address further, that it's not really clear, that you have the resources to address. Sorry, I've been more long-winded than I hoped. So in particular, there's the well-known question of the measure problem. How do you assign probabilities in this kind of context? And they basically argue that nobody has given a satisfactory answer to that, which their opponents accept, but say we're working on it. And given that, the lack of a solution to the measure problem, it's not clear how to make any claims about what's likely based on eternal inflation. So again, I think this is, I'm going to set this aside now, partly because I'm not compelled by the arguments that inflation is generically eternal. And so there's that aspect of the debate that I'm just going to set aside. But I do want to focus on the other questions about the flexibility of inflation and how it fits into fundamental physics. And so if we go back, one of the themes of this talk is that there's questions about inflation that have been persisting in slightly different variations ever since it was introduced. So here's a 1990s version of the question, what is the inflaton? So this is Keith Olive from Minnesota saying, a glaring problem, in my opinion, this is in a review article for basically the first decade of inflationary model building. The glaring problem is our lack of being able to fully integrate inflation into a unification scheme or any scheme having to do with our fundamental understanding of particle physics and gravity. An inflaton is an inflaton and nothing else can only be viewed as a toy, not a theory. So Olive was fairly clearly not happy with just treating something as an inflaton, even though it might be a useful way of exploring toy models. And this is not an unusual opinion. This was fairly widely shared in the literature at that time. I think the way it gets expressed now is quite different. What is the inflaton? And I think the answer would be, it's an effective field theory. Inflation is an effective field theory. And so what we have with the scalar field, the inflaton, is a low-energy effective field theory describing the matter sector, which we couple to Einstein gravity, and that's what gives us our account of structure formation. Now, I think in this case, there's a distinct set of challenges that arise in thinking about how to apply effective field theory techniques in this sort of cosmological setting. So briefly, there's a lot of the apparatus of effective field theories that don't easily transport into this context. So even just thinking about effective field theories is integrating out high energy scales to get to lower energy scales. How do you draw that distinction between high and low energy scales in a cosmological setting in general? You also have, with the expansion of the universe, one way of thinking about this is that you're constantly adding modes as you have your length scale stretching. You could describe that using a time-dependent Hilbert space, but then you have questions about how to describe unitary evolution in that context. So if you want to think of inflation as an effective field theory, you have to make the case that you can, the evolution of perturbations, as I've described it, as a part of structure formation. We can treat this as, in David's terms, a calculation in low energy quantum gravity, because we do have to have the metric coupled to the scalar field in an effective field theory treatment. And we also, the standard calculations assume a particular initial state, that the inflaton field would be in a Bunch-Davies vacuum state. And so we can ask, for both of these, how sensitive are these to quantum gravity effects? So if you have an effective field theory treatment, you want to be able to show that the low energy description decouples in an appropriate sense and is insensitive to the features of the high energy theory. So there are two different senses of decoupling here, both of which have been challenged in the literature. The first is just with regard to the inflationary dynamics. Can we treat these as an EFT that decouples from the UV effects in quantum gravity? I'll get back in a moment to the reasons that people have raised to be concerned about this. And there's also then the question of indifference or robustness to the pre-inflationary state. So how robust is the output, namely the picture of structure formation that we have, or the picture of the universe we have at the end of an inflationary stage? How robust is that to variations in the pre-inflationary state? And this goes back to some of the questions I indicated before. Is this a dynamical attractor? Can we treat the inflationary phase as something that is a dynamical attractor? And are the standard predictions, for example, that you have a scale invariant spectrum of density perturbations with a specific tilt, are those sensitive to variations in the initial state, or are they robust? Let me take the second question first. So in terms of whether inflation is an attractor, this is really, it kind of ends up depending on which type of model of inflation you're looking at. This is something that you have to answer in kind of model-specific terms. But in broad brushes, the form of the results is that you have some assumptions about space-time geometry at the start, and then you have some assumptions about the inflaton potential, or the inflaton field within a patch. And what you want to show is that we have the inflaton field dominate and lead to an effective de Sitter type expansion. And again, this is something that has been addressed going back to the 90s. There are early calculations to this effect. And as I said, the verdicts vary here for different types of models, so there isn't something that you can say that easily generalizes to all of the huge zoo of inflationary models. But Brandenburger, for example, in a recent, well, I guess now relatively recent review, argues that large field models seem to be fairly robust. They do seem like a dynamical attractor, whereas small field models, again, the large versus small, sorry I didn't explain this earlier, refers to how, what the energy scale is of the field at the start of inflation. And so the small field models, in his view, have a more severe initial conditions problem. And again, this is something you'd have to look at for different types of models to assess the degree to which it's a dynamical attractor. And, sorry, I'll wrap up in just a moment. So, and there's been another discussion which goes back to the early 2000s that was motivated by questions about Hawking radiation. The trans-Planckian problem in Hawking radiation motivated cosmologists to also think about a similar issue. So if you imagine inflation going on for a sufficiently long time, then the fluctuations that become galaxies, as you track them back, would have started as an incredibly small length scale mode that then got stretched and grew during the inflationary phase. And for a sufficiently long period, that would have been a mode that's below the Planck length that has been stretched and gives us our kind of structure formation. And one response is, well, obviously we don't know anything about things below the Planck length, so how can we trust an account that requires some assumptions about these trans-Planckian modes in order to be successful? So what justifies treating this initial mode that starts off within what is obviously a quantum gravity regime as being in a bunch-Davies vacuum? A different way of formulating this is what justifies treating a mode as if it's in a bunch-Davies vacuum and it crosses the Planck scale. So this was an issue that was raised in early 2001 by Brandenburger and Martin. There's a few responses here that I mentioned, and I think this also is one of the motivations for something that's come up much more recently, which is called the trans-Planckian censorship conjecture, which is quite controversial and has generated a lot of discussion, and this is something Mike Schneider has written about already in the philosophy literature. So one way of dealing with these trans-Planckian modes is to ensure that they never show up as classical density perturbations, right? So if you're worried about these modes being stretched to a length scale where our ignorance of quantum gravity might affect the predictions, one way to respond to that is to restrict inflation so that it never stretches modes to that degree. So this equation is just requiring that modes below the Planck length don't stretch to the point where they have to be treated as classical modes. So that means that you'd have a shorter inflationary period, and also places constraints on the details of inflation, like the shape of the effective potential. And so this is something that Brandenburger and then Bedroya and Vafa and others have been pushing. It's clear in Brandenburger's case, well, and in the case of the other authors as well, that this is really based on an assumption, based on assumptions in string theory. So one way of thinking about this constraint, it's very similar to the arguments from so-called swampland conjectures. The argument is, if you think of the scalar field driving inflation as somehow derived from string theory, that places constraints on what the form of that field should be. Now, it's above my pay grade to assess how the arguments from string theory are playing out here, but the argument is then to impose a set of constraints on inflationary models. Basically, these are the inflationary models that you could imagine being within a string theory. And the claim, and this is why it's been drawing so much controversy, it actually rules out a large class of inflationary models. If you impose the trans-Planckian conjecture, it doesn't rule them all out. There's still inflationary models that survive this constraint. And similarly, the swampland conjecture rules out a wide class of inflationary models. So again, the thing that I'm interested in this debate is that this is another case of trying to rein in the space of inflationary models by asking how they fit in with a specific proposal for quantum gravity. And there could be other proposals for high-energy physics that would similarly constrain the space of inflationary model building. And I think that's essential to complement the sort of phenomenological success that inflationary models have enjoyed. So let me close just with one last point. Again, this is something that was raised almost immediately after inflation was first proposed. It's surely an act of cosmic chutzpah to use this dismal theoretical failure in understanding vacuum energy and the cosmological constant as a base for erecting theoretical superstructures, but of course this is exactly what is done in current inflationary models. So we use vacuum energy to drive the inflationary phase, and insofar as we don't understand yet how the cosmological constant could acquire the value that it does, it's an act of chutzpah to keep using this as the basis for these models. So, and that's something that obviously I think we need some further insight into quantum gravity and the use of effective field theories in cosmology to understand how to treat this problem as one of the basic problems driving inflation. Okay, so I'll close there and we can shift over to discussion. So thank you for your attention.
Thanks for a really fascinating talk. We'll start with Emily.
Hi.
So it sort of seems as though if you were worried about the inflaton being ad hoc and not doing anything else, you might have the same worries about the inflation field. So does the inflation field do something else, or is this kind of a reproduction of the same issue that it only makes inflation?
It really is the same. I mean, so the inflaton is the field that drives inflation, and so it's really, insofar as that's all it does, then you can only use the cosmological evidence to constrain it. If you had a specific, and I should say that there are, among this space of 200 models, a lot of them do say, there's models that take the Higgs field of the standard model and try to use the Higgs as a way of driving inflation. There's models that take specific elements of, supersymmetric extensions of the standard model. There's a lot of models that do take the form of saying, here's a specific candidate which will identify with the inflaton. And then that gives you a much more constrained problem because all of the constraints coming from the particle physics side then supplement whatever you're doing from the cosmology side. So I think it's really, it's understandable to start off with a toy modeling approach where you just say, let's just see what kind of scalar field we should have that would fit with the cosmological observation. So I don't have a criticism of that in particular. But I think without some other constraints, it does seem like you just have a very flexible paradigm that, and this is a complaint that arises throughout the literature that is inflation just compatible with everything? Are there any things that we couldn't come up with an inflationary model to account for.
So the EFT description doesn't really change that aspect of the dialectic. It's still the same kind of ad hoc problem.
Yeah, I think the EFT approach is more motivated by the idea that it might be demanding too much to say that we should identify it with a particular particle physics candidate, but we could say, is it an EFT that we can treat of as a low energy EFT of some completion of quantum gravity? Yeah.
Thank you.
Just thinking about the origins of inflation. So here's a sort of puzzle about the story you've told, which I can see being resolved in at least two ways. So we have these motivations for inflation in terms of solving a horizon and flatness problem, and then we have a bunch of persuasive sounding methodological criticisms of that from Penrose, from Carroll, from your own previous talk. And the slight awkwardness of that is it's always hard to argue with success. I mean, it turns out that nonetheless, the theory that people came up with by pursuing those ideas then turns out, as you laid out, to be highly efficacious. So, of course, that could just be a huge coincidence. The other possibilities would, I guess, be one, maybe we're being maybe Penrose and Carroll, and maybe you were being too harsh on it, and there's a reconstruction of those arguments that shows that actually they were reasonable. The other and slightly more disturbing possibility is that the situations are sufficiently under-constrained that this model that we had in mind for fallacious reasons nonetheless has been able to be sort of contorted into being very useful in this space.
Right.
Would you just sort of say something about how you think about that?
Good. No, that's a very good question. So let me amplify the worry a little bit. So here's a way of putting the worry. We learn more and more about the universe. We keep extrapolating backwards until we get to the point where physics is almost completely unconstrained. And then we start creating models that account for all the properties we've observed, right? So that's a worry, that if you really think of this energy scale as, so there's sort of two aspects of the worry. One is something I mentioned in passing before, which is, I think there's an interesting question, like, at what energy scale do you expect to solve which problems, right? And so one of the things that's always struck me about inflation is that it treats a bunch of problems as a package deal. And a lot of the alternative theories, so the defect account of structure formation, most of the alternative inflation models now, don't treat everything as a package deal in the same way. And that's it. What I mean is they don't try to solve the horizon, flatness, structure formation, all those other problems with a dynamical phase of evolution all at once. They solve the different problems in different ways. And so that, in part, I think, so that there's just the worry that you're exploiting the flexibility once you get to the energy scale where you can start doing more free model building. But I think the fact that there's that divergence, that a lot of the alternatives sort of separate out components of what inflation tied together, in part answers your first question as well. Namely that, so there's just the observed facts. Any theory of the early universe has to be compatible with the isotropy of the early universe and with the uniformity of the temperature and so on. But it isn't the case that they have to do that by changing things in exactly the way inflation does. And the fact that all these alternatives sort of break apart that package, to me indicates that for some parts of the community, the case that they should be treated as a package deal was not actually that compelling. Now, on the other hand, I could also just be overplaying a skeptical argument. It might just be the case that I'm wrong and being critical and that Penrose is wrong and so on. And it might have been that they've discovered some deep truth that led them to the true theory. But I also think there's a lot of cases in history of physics where really sketchy ideas led to very productive work. So Mach's principle helped Einstein discover general relativity, but it's not clear that we should accept Mach's principle. Right? So I think I'm usually a little bit more skeptical of the sort of methodological principles, but I don't want to then say that they can't lead to good theories, right? It's just that there isn't such a direct connection.
No.
Yeah.
Chris?
Thank you. But the last thing you said, I think it's clear we should not accept Mach's principle. It's a compelling idea, but it turns out to be wrong.
Yeah.
Anyway, my question is sort of more an aside in your talk, but I'm intrigued by your, short remarks about eternal inflation. And I would like to invite you to expand a little bit there, because you mentioned that the majority of the practicing inflationary cosmologists are basically convinced of eternal inflation, but really for problematic reasons, or somewhat insufficient arguments. And so this raises the obvious question for me: is why is that? Do they not recognize the sketchiness of their motivations?
Yeah.
Is it not something that's debated? What exactly is going on there?
Good. I mean, I think I'm probably more cautious in this case. So I'm more confident that I'm right in being critical of the initial fine-tuning motivations than I am in being critical of the consensus on eternal inflation. So this is partly just because I've talked to people who are advocates of eternal inflation. I've read a lot of the work, and it hasn't convinced me. But it also might just be the case that I haven't yet fully grasped, the most compelling argument. And this is something I haven't had the stomach to look into. The reasons for my skepticism, with that grain of salt in mind, are essentially that the arguments that you have inflation leading to this sort of global structure where you have eternal inflation, where you have different pockets of the inflating universe, seem to all rely on extrapolations of semi-classical physics, or even just the kinds of arguments that you get in slow roll inflation, which is really there's a kind of way of treating these arguments that is very hand-wavy. It seems to be extrapolating those into a domain where I just don't see why you would trust those arguments. There's a separate, and it's really, the arguments, one form of the argument, going back to Vilenkin, I think, is that if you imagine, if you have a slow roll potential, and you have the scalar field rolling down the potential, then you can think of it as like a diffusion problem where quantum fluctuations will cause the inflaton field to move back up the potential. And so the account of eternal inflation is basically comparison of the rates at which you would slow roll down versus the quantum fluctuations back up the potential. And the argument is that if you have a sufficiently flat potential, which you need for other reasons, you'd expect that the quantum fluctuations would keep driving the scalar field back up the potential. And so then you'd have regions where the universe is continuing to inflate, and then some regions where it rolls down the potential to stop inflating. So you then have bubbles within an overall expanding universe. So the question is, how much do you trust those calculations? And then there's a different kind of question, which is, what are the original motivations for considering eternal inflation? And I think it's really the kind of question that I am interested in. How do we think about the pre-inflationary state, and what kind of pre-inflationary state would make sense? And they're posing that question, but then ending up with this very different answer. And I think there's an element of so in Linday's work in particular, when eternal inflation was first introduced, there's a kind of, what I see as a bad answer to this foundational question. So one way of putting the foundational question that he was responding to is, it's kind of a second order fine-tuning problem. So you first say the standard Big Bang cosmological model is fine-tuned because you have to assume that you have a uniform patch that has all these properties. You can then ask, why do we have an inflaton field with the right potential and the inflaton field in the right starting point in order to generate what we see? And one way of responding to that is, well, we have a huge universe. There are different regions of that universe where the inflaton potential has different forms, and the inflaton field starts in different positions. But at least in one of them, or there's a non-zero probability that there's a region where it starts in the appropriate conditions to trigger an inflationary phase. And so I just think of that as a very weird, or sort of not a compelling answer to that question. And so I think some of the reasons why people want to have eternal inflation, I find not very compelling. Although, as I said at the beginning, take it with a grain of salt. Like, there might be more compelling arguments that I just haven't tracked. And in particular, there's a line of work from string theory that motivates this kind of picture as well, which I just don't understand well enough to really assess.
Coming from David.
Yeah, I mean, I don't know this picture very well either, but I mean, just to add a bit of heuristic as to why I think, what I think makes the arguments look more plausible. I mean, here's a very broad general case of why people think it's hard to avoid eternal inflation, as I understand it. Things tend, annoying and awkward things that break your model tend to be disregardable if they're exponentially suppressed. If I have fluctuations that are exponentially suppressed, normally I can say, fine, there won't be any fluctuations. But I've got an exponentially growing space-time, or space rather, and exponential growth is just, as we found in the last 2 years, exponential growth is really fast. If you've got an exponentially growing space, then even exponentially suppressed things that stop inflation stopping aren't strong enough to turn inflation off aggressively. You've got to turn inflation off so aggressively that there are no even exponentially small regions in which you fail to turn it off. Because if there are, they'll just exponentially grow right back again, and you've got to continue to have inflation. I mean, that's my understanding of what the sort of the heuristic underlying of the calculation arguments is.
I mean, I think that might be a heuristic, but I think it's really looking at the scalar field evolution, and that I would say it's sort of the opposite, that you have exponential growth everywhere, and that it's the question is, how do you stop it in some places? And so it's really, how do you get the scalar field to get to the point where you slow down and change into FLRW expansion? Maybe I'm saying the same thing, but
yes, I agree with that, but the problem is, whatever that mechanism is, it now needs to be, it doesn't just need to turn inflation off, it needs to be so aggressive
that it turns inflation off everywhere.
That, that there aren't even exponentially small places where fluctuations stop it working. I mean, normally we wouldn't care about that. If I have a mechanism to explain a phase transition or something, and there's a sufficiently large quantum fluctuation would break it, then you're going to say, fine, those are exponentially suppressed fluctuations. They're not going to happen at all. If they're going to happen, they're going to happen in some microscopic patch that's then just going to get squashed by all the other stuff around it. If the whole thing's exponentially growing, then those arguments don't work anymore, because the however little patch in which your mechanism fails, it's just going to exponentially blow up. So a mechanism that across the whole space just slams inflation off so aggressively that you don't have these exponentially small bubbles that just blow up again, that's really hard to do. I think that's the...
Yeah, that might be right. I mean, the other question though is, I mean, the basic question is, why do we care about the regions elsewhere, and how does that enter into our assessments of what happened in our own past lifetime? Right?
Sure. So there's a conceptual question: why should we care about internal inflation? Has internal inflation applied to these fine-tuning problems?
Yeah.
Are people over the sight of internal inflation? And I think there's a lot of good reasons to be skeptical. And I think separate that out from just the calculation.
Right. Yeah, no, they're two separate issues, definitely.
Thanks, Chris. I was going to ask other Chris's question, but then I guess I'll ask something else. So you briefly mentioned reheating, and this is just something that I genuinely don't know much about. I'm curious, what's your take on the scientific status of reheating right now, and to what extent does it figure into? Because my sense is that it's not very established, but maybe I'm wrong. And so I'm wondering to what extent it figures in these debates about the flexibility of inflation, etc.
So I'd be curious to hear from other people in cosmology in the room. My impression is that there are models of reheating, but I think they're really, really under-constrained. And I don't know how much people see that as one of the problems with inflation. To my mind, it's a big one, right? Because it really makes it look like, and just to elaborate a little bit, it's not just that you don't have a model of reheating, it's that your account of structure formation, your account of reheating, seem almost completely independent, right? So I constrain a bit of the potential here, and then the bit of the potential here, and the interaction term in Lagrangian. Those seem like completely independent things that I can fix in my inflationary model. And as long as that's the case, it does look that you just have a flexibility in the model building. But if anybody who has looked at reheating more, yeah.
Yeah, I mean, the reheating, I think that is the least of the problems with inflation. Okay. The problem with reheating is that very much model dependent. We cannot have a kind of generic model for reheat. So basically, the whole idea, you write down the potential. There are many terms. So you freeze some of them, you keep one, which is going to give the inflation, and then at the end, you just turn on by hand the other terms. Is the terms through the interaction of the input and potential, they are going to give actually the radiation and make it clear. So that you have to do it by hand again, but it's model dependent, it's not a generic one. So, I mean, there are models people have worked on that, and I think, I mean, this is a problem, of course, how you go from the cold phase to the radiation dominated phase. So again, it's reconstructing appropriately the potential. But I think many of these models have, so to speak, passed this test. Now the question is that when you hit the universe at that point, you don't want to create phase transition that can give you, for instance, domain walls or monopoles or things like that that they are going to lead another catastrophe. So it is a cooking thing. But for me, most important problems are before, before that. But again, so I don't want to interrupt you because you asked us.
Yeah, no, I've looked at it a little bit. There is one thing I'll add, which you mentioned in passing, but I mentioned that once the sort of perturbations are imprinted early, then they're preserved. Some of the models of reheating can mess that up. So that's another constraint, that you want to make sure that the horizon exit and reentry creates a set of density perturbations, and that those properties are preserved through heating. And so that's a further constraint on reheating. But yeah, I think of it as, yeah, in some sense you have models, but it's not maybe all that compelling. But yeah, go ahead, sorry.
I guess just to complement, even the models that don't spoil the scale invariance of the core spectrum of the inflaton field, they are still toy models. Like we don't have any realistic working model of reheating at all. So it's quite a, you have this map of the inflaton field that happened in the first second of this universe history, then there's another map 300,000 years later, and we just say like, yeah, they must be the same somehow.
Right,
they're easily related.
Right.
It's kind of like, yeah. I think it's a bit absurd to claim that at this stage.
I've got a question from Joanna.
Thank you. When discussing the EFT approach, you mentioned that one of its problems is that, here I'm not sure if I understood correctly, is that there is some difficulty in distinguishing low and high energy scale in cosmology. Could you explain this?
Yeah, so if you have an expanding universe, if you don't have modes that are evolving adiabatically, you can have them cross energy scales just as a result of the expansion. So you don't have you don't have the kind of structure that gives you a clean separation just between high and low energy modes, although you can have it in some cases, or if the time evolution is slow compared to the modes you're looking at, then for periods of time you can draw this distinction, but just in general, because you don't have the kind of symmetries that allow you to draw that distinction.
Mike?
Hi. I guess I was going to ask questions having to do with the reheating discussion, but I'll ask a different thing now. So earlier in either reaction to something David said, or maybe it was just in the ensuing back and forth, you re-emphasized something that interests you, is that in inflationary cosmology, we have this sort of package deal for a lot of problem solving at a scale, or the inflaton scale. And in the other various alternative approaches that have cropped up, there's sort of a more libertine attitude towards problem solving, you sort of piecing together. And I wonder if you could comment at all on this in relation to the like singular structure of the sort of ambient like quantum cosmos that the inflaton is supposed to be situated in, or in these other alternatives that often have sort of very dramatically different global structure, specifically with regards to the Big Bang singularity.
Well, certainly your view of what emerges from the singularity, or what emerges at very early times, will determine what problems you have left to solve by the time of, say, the surface of last scattering, right? And so I think in the early formulations of inflation, it was very much like Misner's view that what emerges from the singularity is a chaos, right? And so then you have to have some subsequent dynamical evolution that explains all of the properties, in effect, that we see in the surface of last scattering. And just to emphasize one thing I said, I think last time, that view doesn't necessarily map on cleanly to inflation as a research program, because Starobinsky's view in 1980 was the universe started just as a de Sitter solution, right? So he made a specific proposal about what the state was at, and that in some sense he also wanted to avoid a singularity. So you just have a de Sitter solution that then transitions into FLRW expansion. And so he gave an early account of inflation based on that idea. So in that case, there isn't any commitment to a chaotic beginning. But I think in standard ways of thinking about inflation, that's usually the view. And then that motivates the need to solve all these problems at a later dynamical phase. But I think as we have other proposals for quantum gravity, we might just say, those aren't problems that you need to solve at that scale. So if I have a proposal for quantum gravity effects, that could obviate the need to have something happen at the energy scales where inflation is thought to take place. That produces certain features that we see in the CMB.
Can I ask a quick follow-up? So there's something peculiar in part of the dialectic, not yours, like in this area of research, which is, on the one hand, a lot of people working on alternatives to inflation seem to be proud of the fact that they are also concerned with Big Bang, with a singularity. But then the way that they inevitably propose to problem solve a suite of problems that now includes a bunch plus the Big Bang is to help themselves to a variety of scales, or just go for a complete package of a cross energy spectrum. But then within inflation, you have this suite of problems being solved all at one scale, and it's precisely that we're focused on that one scale that we're putting off this further problem about the initial state. And that seems very, is it a problem counting difference, or is it a like focus of research difference between the two? Or?
Again, I think there's different views about this. So, there's hundreds of inflationary, people working on inflationary cosmology. So I think there's probably a pretty wide spectrum of views. But I think, again, looking historically, there are various points where people, I think, were quite hopeful that they could ignore the subtleties of quantum gravity. That they would have very weak constraints on what the pre-inflationary state had to look like, and that it was an advantage that they didn't have to wait for their colleagues to figure out quantum gravity, that they could do all this at a lower energy scale. There are other people, though, who have argued that, and this is why I said there's one slide where I said it's a problem/opportunity. There are other people who've argued that, well, if you think about inflation carefully, what it does is magnify, small, perhaps sub-Planck level effects. And so you would actually have to have substantive assumptions about quantum gravity. This isn't just a trans-Planckian problem, but even going back to the early 80s, people were saying it's really a magnifying glass. So if the initial space-time geometry had some interesting quantum gravity effects, inflation would magnify those, and so then that would actually allow us to have some insights into quantum gravity. So I think there's, sort of conflicting views about how those relate.
Guy, I have a quick comment on the question.
Yeah.
So about this argument about so this package deal argument, I don't quite understand, because the cosmological model has 6 independent parameters. Only 2 of them are related with the early universe scenario, and they don't tell anything about the dynamics that was going on. So I don't think that inflation somehow has a package deal that the other models don't, because at the end of the day, all of them have to give you basically the amplitude and the scalar to tensor ratio, and that's all. So we don't have access to what really happened at the beginning anyways. So I'm a bit puzzled about that argument of inflation being a package deal as opposed to the other models not being a package deal.
What I meant is just in terms of the sort of mode of presentation. And so David was taking me to task about how is it that this bad idea led to such good results, right? Or are you wrong in claiming that it's a bad idea? And I was arguing in effect that part of what the other views do is say, we're going to set aside those problems in the way that inflation solves them. And as you say, really just focus on getting NS, right, and the amplitude. And so if you're able to do that separation, that means that at least the people making that case don't see the other aspects of inflation as essentially linked to the account of structure formation. So that supports the idea that these other problems aren't necessarily a good guide to theorizing. But I think the way inflation, again, this might just be more a matter of textbook presentation. You say, why is inflation a good theory? Because it solves, sometimes it's three problems: flatness, horizon, and structure formation. Sometimes you throw in a monopole problem, sometimes it solves a singularity problem. So you sometimes get this whole sense of a package deal. And that, I was characterizing it more as a mode of presentation. I didn't mean to endorse it. Yeah.
And the question I had, I wonder if you could comment more about this borderline case between accommodation and prediction for inflation.
Right.
And if you consider accommodating weaker than predicting to evaluate a theory.
Right.
Because I'm a bit afraid of historical contingencies playing a role on how we evaluate a theory to be better or worse than other theories.
Good. No. This is good because so the reason why I think it's so the reason I get frustrated when people just say it's an unambiguous prediction is because it's actually kind of a Pyrrhic victory for the early models of inflation, because they actually had to throw away a lot of the early models in order to accommodate the constraint, the amplitude of the structure of the density perturbations forced on you. So I think if you say it's an unambiguous successful prediction, you miss that. Now, in terms of prediction versus accommodation, there's one way of cashing that out, which I think can't be right, which is a matter of what a certain individual historically knew, right? So I would say instead it's a matter of the structure of the theory and sort of whether you're using a fact as an independent constraint on a parameter. And so you could have cases which, and so in that context, I don't think it's actually particularly important. So Mercury's perihelion advance was known to Einstein before he came up with GR, but it's actually a much more sensitive test of the structure of the theory than the light bending result, right? And so I'd say that just in terms of how much you understand the details of the theory and how much you constrain the details of the theory, that's the important factor. And the actual historical evolution is not as important.
Yeah, because as you said, inflation loosely defined as this accelerated expansion of the universe in the early stage. I'm pretty sure you can hook up any potential that can give you any R and NS.
Yeah.
Any particular tilt as well.
Yeah.
And so from that point of view, inflation can only accommodate in that sense.
Yeah. No, and this is, there are people who proved theorems earlier, give me an R of T.
Exactly.
I can write down an effective potential that gives you that.
Exactly.
Yeah. And then you can try to constrain it by saying, there are various people who have tried to say this, well, let's characterize how complicated a potential is, say, in terms of how many kinks it has or something. And then you could try to impose, if we only have simple potentials, then that would constrain the kinds of evolutions that you can describe. But yeah, if you just leave it as an effective potential, you're replacing the scale factor as one function with a different function, which is the effective potential.
Okay, but a question from David, and then one from Enrique. That's fairly brief, so we don't go too much over.
Yeah. And I'm interested in how much more data we're going to get. It would be nice to hope that, the equivalent meeting to this 30 years ago, I'm sure Chris is still running these schools, we'll be talking about how the revolutionary data is collected by whoever satellite in 2037 gave us a much deeper picture of it. But I'm not sure that's over-optimistic. It's not clear to me how much more cosmological observational data is going to come in that's going to constrain the problem.
So there's the sort of in-principle question and the in-practice question, and the people who actually know what observatories might be planned would be able to answer the in-practice one better. But you could always hope to detect the gravitational wave background. That would give you insights into this R, the scalar to tensor ratio. And a lot of the current alternatives to inflation give you different predictions for that. So that's one source. You can see that as well in the polarization, the B-mode polarization of the CMB. So that's one thing that people, I don't actually know what the current best options are, but I think there's South Pole observations that are trying to look at the B-modes. And I don't know how much possibility there is for non-gassy entities. That would be another thing, but I think those are expected to be pretty hard to observe. So I think probably the B-mode polarizations is going to happen. I don't know how much they'll tell us. And then if there are other options like the gravitational wave background, but I don't know if that's actually feasible. That might require LISA or something like that. So, you know, if we get a space-based laser interferometer, then we might have the answers.
Considering in other contexts, our threshold has been particle acceleration inside the solar system. I'll take away from the least
Right. But sorry, anybody else who knows more about this can chime in. I'm not really up to date on what observations.
Yeah, I mean, the polarization kind of measurements will be made, and that will clarify differences between the models.
Mm-hmm.
So there are some models like, you know, string big bang or string gas, whatever, that they give a red spectrum, which is not going to be in agreement. It depends what will be, you know, the result.
Mm-hmm.
And then it's also some issue with non-Gaussianities, because there
Right.
are models that give non-Gaussianities. Also, if you take multiple stages of inflation, again, you're going to have non-Gaussianities.
Mm-hmm.
So that will be, I mean, there is a model that I will briefly discuss afterwards about from a string theory with interactions of brains, and they predict non-Gaussianities. So
okay.
again, is with that. I mean, you know, so then there have been constraints on different models from gravitational waves with electromagnetic counterparts. So from the difference that you have between, you know, when we go to the electromagnetic signal, the gravitational waves, again, constraints have been put to some models. So for sure, constraints they will have. So, then often what we do is just to predict the model that can accommodate some of that, which is not correct. But for sure, constraints they will have.
Thank you.
Okay, I'll try to be as quick as I can. So I was just wondering if you think that the Starobinsky model of inflation, right, which as far as I understand, which is not a lot, can be basically understood purely as a matter of higher curvature corrections to general relativity. If this fact can somewhat help with some of the questions you're asking, the foundational questions that you're asking, especially regarding like what the inflaton is, and like what is the status of this model.
Yeah, no, I think it's much more appealing. The Starobinsky model was just an R-squared correction of Einstein-Hilbert action, and that seems like it's much, I mean, that's well motivated in some ways. I don't actually know, I don't know enough about the model to say that the best way of treating it is still the way he originally proposed it as an R-squared. I mean, I think a lot of people call something a Starobinsky model now, which they think of they treat it as a scalar field with a certain form of effective potential, but if you can still describe it as something that follows from a proposal for quantum gravity. I also have to admit, I don't know what people in quantum gravity think of an R-squared modification of the effect of the Einstein-Hilbert action, whether that's still a really viable model. But in general, if you had something, a motivation like that, where you said, here's a correction to the Einstein-Hilbert action that leads to an inflationary phase, that's appealing. So I don't know about the details of the way Starobinsky did it, whether that still stands.
If I can just something
go.
about that. So the Starobinsky model is indeed appealing. However, any attempt to derive Starobinsky's model for quantum gravity proposal has failed.
Okay.
And what it happens is often you get Starobinsky model with a different sign in the higher order corrective, which gives you ghosts.
Yeah, so you get instabilities. And,
So Starobinsky model works very well with the data. Is to my mind is quite plausible, but we don't know where it comes from either. So that's the problem with it.
Yeah, good.
Okay, John, again, thank you, Chris.